Hello everyone. Today I'll be talking with you in this video about general introduction to PLCs. So I'm going to be going over each one of these topic questions here. Number one, what is a PLC? Number two, what can a PLC do? Number three, what kind of jobs can I get with PLC skills, which is a very relevant question. Number four, why do they use PLCs instead of a computer? Then next I'm going to go into a subtopic area, which is what is digital logic? Okay, this is for programming PLCs. What is digital logic? You're going to need to have to understand basics of digital logic in order to be able to program a PLC because it's based off of that. Next, number two is what is relay logic? Next, what are the ladders in a ladder logic program? And number four, how to read or construct a ladder logic diagram. So I'm going to go ahead and erase all of this in order to make room. And we're going to start with the first question that I want to go over here, which is, what is a PLC? Well, a PLC stands for Programmable Logic Controller. So basically, any PLC is going to be some input terminals and then you're going to have some output terminals. And based off of what is the input states of these input terminals, whether they're on or off, you're going to get a response that controls the output terminals. And what they usually call that is actuation. It's just a fancy word to say control or how you energize things that are connected to the output. So that's basically what a programmable logic controller is overall. These inputs are going to either be a on or off state, which is the same thing as 1 or 0. On would be 1, 0 would be off. So if you hear the terminology, you can pick up on that and know exactly what they're talking about. Sometimes they use true or false as well. So a true is a 1, which is also an on state. A 0 is an off, which is also a false state. And so generally speaking, that is the overall point of view of what a programmable logic controller actually is. So it's just a controller where you have terminals that are going to output different on or off states. Next, what can a PLC do? Well, I kind of already somewhat to a certain degree covered that. A PLC can basically, in response to what's put into it, control things that are connected to the output of it. Now, those things could be simply it's just as simple as turning a motor. I'm going to make a diagram here. Turning a motor on or off. And say like you have a switch over here and you have some voltage going to that switch. Say that voltage is 24 volts, which is very common for PLCs. And if you close that switch and you tell the PLC, okay, this switch is closed, depending on the program that's in here, it's either going to turn that motor on or off, or perhaps maybe do nothing at all. It depends on how you program it. So that is what a PLC can do. Next, what kind of jobs can I get with these PLC skills? Well, the type of jobs that you can get are usually in automation for manufacturing processes. So what that means is that most of the time factories make use of PLCs to control their manufacturing processes, And if you know how to program a PLC, that's of a great use, a great utility usage to them, and your prospects for being offered a position goes up as you know how to program PLCs, because they work with big industrial heavy-duty equipment like motors or very large lightings, networks, or safety. Safety is a big part of it, because when you work with big energy, you're going to need safety. So usually they have safety applications of control with these PLCs. So next, why do they use PLCs instead of a computer? Well, a PLC is a logic controller, so usually this PLC is not very big at all. A lot of them can fit basically about into the palm of your hand, and so it's actually, overall, it's a microcontroller. A microcontroller is different from a microprocessor. A microprocessor is something that's very general, that has much wider range of applications. A microprocessor is what you have in your computer, so you can basically take different programs and load them onto your computer, and your computer can do all kinds of different things. But by contrast, a microcontroller is a controller unit that is dedicated to the specific purpose of controlling. So you don't have that flexibility with it. But unlike the microprocessor, since you don't have the ability to do other things on it, it's more dedicated to one specific purpose, and therefore that makes it more reliable. So the reliability of a PLC is very high when it comes to control applications. And to give a specific example, I'm sure that we've all had that condition where we're clicking through windows on our PC and we get a frozen window or something, and the computer freezes up and you can't do anything about it. Well, when you're controlling manufacturing processes, that's the last thing you want, is for control to be suspended and it be stuck in a certain state where the controller isn't responding. So since you don't want that, what you do is you make a dedicated device to control itself, which is this microcontroller overall, which is the PLC. That's why they use the PLC instead of microcontrollers. Now next, we're going to go into our major other subtopic area here, programming a PLC with ladder logic. Okay, so the first question is, what is digital logic? Okay, you're going to need to understand what digital logic is, because that's the basis by which PLCs work off of, and it's really not that complicated. When you look at it, it's common sense. It's quite intuitive. And so digital logic is a logic that they would call in programming conditional basis, a conditional construct. So the digital logic just says that, and you'll find this in a textbook, like an AND gate, and you'll have an OR gate, and then you'll have a NOT gate. This is the basis for all digital logic in all computers, whether it's microprocessor or microcontroller. These are the three basic fundamental elements in everything, even in memory structures. These are the three basic elements, and just by configuring them different ways, you get different functions. So for the AND block here, we have this is AND. What it says is that if I put one here and one there, then I would get something out of here. So a 1 here and a 1 here gives you 1 there. So if I turn on a switch here to this terminal, the input terminal here, and I turn on a switch here to this input terminal, then I will get an output. But if I don't do that, instead, if I only put a 1 on one of them, or or the other, I won't get an output. And of course, if you don't put an output on any of them, you don't get an output. So in other words, it's self-explanatory. It's just to say that you need a 1 here and a 1 there in order to get an output. So it's the AND function here for this gate tells you what you need to put in order to get an output. The OR function says that is defined to be that if you put a 1 here or a 1 there, then you'll get an output there. So it only requires one of these to have a ON going to it, not both of them, and then you'll get an output. This next gate is called a NOT. So the NOT gate is also called an inverter. All it does is it does the opposite of what you put into it. So if I put in a ON state, a 1 here, it's going to invert it and it's going to give me a 0 here. If I don't put anything here, it's going to give me a 1. So how does this all relate to our next topic here? What is relay logic? Well, relay logic works off of the same basic fundamentals of those digital logic functions that I just went over. But first we need to know, what is a relay? Well, what a relay is say we have a voltage source here, and if we have that voltage source and we want to control something really large, say there's 480 volts AC running a motor, and we want to be able to push a button and turn on that motor. Well, 480 volts AC is very large, and there's a potential that you could get shocked from it. So you don't want to shock, or you don't want to be electrocuted by 480 volts, because at that level it's a health hazard. It's a threat to your life at the very least. So what the point is of a relay itself is to be able to control things that operate off of large energy with small energy. Okay, so let's say you have 24 volts here, and you want to close a switch, and you want it to turn that motor on. Well, what you would do is you could have a switch here, and then you have your motor there. Then that's going to ground there. But you have a switch and you have your motor there, and you have a coil here. Now that coil is going to have like some kind of a metal there. It's going to be like a bar, and what it does is it makes that bar a magnet, and so it's going to be linked to this switch over here. Now when I close this 24 volts here, you're going to have electrical current go through this circuit here, and when it goes through this circuit here on the left hand side, it's going to make this a magnet. It's going to be an electromagnet, so you can either magnetize it or demagnetize it depending on how you push that switch, whether it's closed or it's open. And so that magnet is going to pull on this switch over here that we have on our right hand side, and that switch is going to be able to close, and then now without touching it, we are able to switch on power to this very large motor here that we have for 480 volts AC. Now, where does the relay logic come into this? Well, suppose I had two switches or two conditions. You can see these switches as being conditions now. If I had two switches and I closed one of them, well, it's still not a complete circuit. And if it's not a complete circuit, then nothing will happen over here because we have no energy flowing through our circuit, and this is not a magnet now. But if I closed both of them, then what would happen? Well, we'd have electric current through here, and then now we would have a electromagnet. And so in doing that, what we can automatically pick up on here is that this is an AND situation. Remember our digital gate that we had there before, our digital function for AND? What it requires for an output is that both of these are, these inputs are high, those conditions are met, and then we have that AND function. Now by contrast, if I had two switches and I put those switches parallel to each other so that one switch or the other would energize this coil, again, I just said it in the description, this switch or this switch will energize the coil. Now we have an OR function. By contrast, if we had a switch that was always closed and we had to do something to it, we had to pull on it or we had to push it in order to open it, that would be what a logical NOT function would be. So in other words, if we did nothing, we'd get a 1 there, and then this would be energized and it would turn on that. If we pulled on a switch or pushed on a switch, whatever is needed to open it up, then that means we're putting in something and we'd be getting an open switch, and now because of that, the motor would be off. So that is what relay logic is, and so that's the primary basis for programmable logic controller diagrams. So perhaps we went over quite a bit here, but if you can basically digest that, then pretty much you've opened up the whole entire door to understanding programmable logic controllers, and you have a very, very, very good basis for getting very good at understanding these programmable logic controllers. Everything else after that are really just extras and really just understanding a little bit more about digital logic, but you have to understand this at the very least. Okay, so next, what are the ladders and ladder logic diagrams? So in ladder logic diagrams, what we have here really is we have a computer program inside of that PLC, and when you go to program it through what they call an IDE, Integrated Development Environment, that's a really large word, it's a big word. All it means is that it's your way of programming the PLC. You're going to be using a program to program the PLC. And when you go to program the PLC, you're not actually going to be typing in text in words or anything like that. What you're going to be doing is you're going to be placing symbols in different places in a ladder diagram, and that's going to form your functional basis for control. So in our ladder diagram, they call it a ladder diagram because it looks like a ladder. It looks like this. And they call each one of these lines going from left to right, the horizontal lines, they call those rungs of the ladder. And so ladder diagrams came from basically from an electrician standpoint background, because it used to be in the old days, really, really older days, they used to do controls with actual relays itself. But now, since we have microcontrollers that can actually do the same functions, what they do is they use the same type of symbology to symbolize relays. So that's where you have this overlap of relay logic and digital logic, where they're actually two different ways of doing the same thing. So they call these the rungs of the ladder, and so with them being the rungs of the ladder, the program actually scans and it goes past one rung each time when it does a complete scan. So it looks for what are the conditions of this, it reads that, and then it goes here and it reads that, just like any other computer program. It reads it line by line. A lot of computer programs actually go from right to left, but that's just extra information. We're not going to get into that. But anyhow, it's going to read each one of these rungs for the conditions that are on them. So if we have here what we call a relay contact, that's like a switch either being open or closed, okay? What we'll have on the other end is we'll have a relay coil, and that's the symbol for that. So this is a contact, and then this is a coil. Now the difference between that is that, well, contacts can come from being wired to, say like this is your PLC again. Contacts can be wired to inputs on your PLC. And so if I pressed a button that energized this terminal on the PLC, now what I would have is I would have a closed contact. In the PLC program, it doesn't actually animate it and actually close it, but what they will do is they will animate it by highlighting it, so you'll know that it's closed because you see that it's highlighted. It either illuminates to be maybe green or some other color, or it's not illuminated and it's like a on or off condition. And so that's the animation that they offer you in these programs. So the contact, if that's closed and this is voltage here, then what it'll do, the idea is that it'll go through this contact and it will energize this coil. That means the coil is on. Now the coils can be connected to an output. So you have your output over here. This is your input. And the output can be connected to a coil. So you can just simply, as a very basic first program, you can just make a condition like this where you hit a switch and then you get an output. Now, if I double this up and I have two contacts that are in series with each other, remember like our previous example, what we will get is our AND function. So it'll require two inputs. Say this is input 1, and then we're going to label this input 2. Then it requires both of those in order to get an output there, which is connected to the output terminal to turn something on or off. Then the next thing, if we had a contact here and a contact here where they are connected in parallel, what we would have is the OR function, because in order for this voltage to get over here, say this is ground, in order for this voltage to have current go through here to ground, it's going to require this to be closed or this to be closed, and that's an OR function. So that would be actually your second function. This is just a basic on or off switch. And then next and finally, for our NOT function, what we'll do is we'll use a contact that is usually closed. Now, in industry, they usually call that normally closed. So these would be normally open, and this one, with this line drawn through, it means normally closed. If it's normally closed, then it means that this is on without any button being pushed. But if I push a button and I energize the input here that's connected there, then it means that it's going to open it up, and then this is going to be de-energized. And then if this is connected to the output, then it will turn off. And so basically that does it for ladder logic diagrams. And so that also pretty much covers the fourth point that I wanted to cover here, is how to read or construct a diagram. Obviously we just constructed it, so we automatically know how to read it. You're just going to go through it line by line, and you're going to say, okay, if this is, you know, energized, then what's going to be the outcome of this? And you go to the next line and you do that. And so one other last note is that these what you call them, contacts and coils, they don't have to go to inputs and outputs. They can be referenced to other things inside a program. So say I'm referencing a contact here, and this coil is connected to an output. This coil here is just in the program. So we'll call this switch 1. We could use SW1 as just a description of it, a descriptor. And say we have a label for this called A. And then this would be, say, like a motor 1. If I energize switch 1, it's going to energize A. And then A is going to energize this A, this contact here. So that's like having a relay. This is SW1. Always try to visualize this when you're doing it. That'll provide you with a better understanding. And if we have this going to, say, like our switch here, okay, then energizing A may not directly energize the motor, but indirectly it'll energize something else that energizes the motor. And so what we would have is we would have this being switch 1. This is a coil. This coil would be A. This is a contact. Contact A would be referenced to A here, so this would be A. And then this is well, actually we have a coil, but this coil will be connected to, so it will be like that, and it will be connected to say like our motor here, M1. Running out of space there on the board, but the idea is that switch 1 will activate this coil, and then this coil will activate this contact. This contact will activate this coil, which is M1, and M1 will be connected to an output here, which also has a loop with voltage and current flowing through it. So that is complicated, and you wouldn't have to do that just to turn on a motor, but it does give you a lot of flexibility in how you can design things with a PLC. It's really all about combinations at that level, at that point there. And so with that being said, I think I've covered the last point there, how to read or construct a diagram. And so that'll basically do it for this general introduction to PLCs, and hopefully this video was helpful for you. Thank you for watching, and have a nice day.